Hi, everyone. I'm Ethan. I'm a software engineer at Google, and I'm working on making hardware easier to build for everyone. At Google, we've seen how the growing demand for compute has outstripped the ability for the silicon industry to provide it. With new applications in machine learning and simulation, it's more important than ever to talk about custom silicon and how it can improve your projects and businesses. Historically, building silicon has cost millions of dollars and taken years of time. I'm here to talk to you about how Google is trying to reduce this cost to thousands of dollars in just weeks of time with our open silicon strategy. At Google, we believe the only way to open up the silicon industry is to build an open source tool chain around it. We're interested in building an open source community in the same way that GNU, GCC, and LLVM built a community around software. We're here to enable companies and hobbyists alike to build completely new kinds of products and applications with silicon. We love experimentation at Google, and we want everyone to be able to experiment with hardware the same way they do with software. So, building silicon in this new way is going to be very exciting and different. We're targeting multiple open source tools. We're looking for fast iteration times measured in minutes. Open source manufacturing data so that you can get started right away without asking anyone for permission. And we're looking to do this all with Bazel to coordinate them. I'd like to set the stage with a few definitions so that everyone can understand some of the terminology in this talk. RTL, in the same way you think about C++ encoding your logic and a compiler targeting a particular CPU like x86. RTL is the equivalent of a hardware programming language. You encode your logic and control into a language much like you would with any programming language, and then a silicon compiler will target a particular manufacturing process to turn that into real transistors. The first step of this process is synthesis. These tools will take your RTL, which is again just like a hardware programming language, and turn it into abstract representation in terms of gates and transistors. So things like multiplication, addition, ifs, and ors all get turned into individual transistors and gates. Then it's our place and route tool's job to take this abstract representation of our circuit, which looks a lot like a graph at this point, and put it on a virtual silicon wafer. Because a silicon wafer is flat, we have to figure out a way to put all these elements on our virtual silicon without them overlapping or breaking any of the rules of the manufacturing process. And our place and route tool will give us a GDS file back. This file is what we hand off to the manufacturer to actually harden our silicon into something real and tangible. So graphically, this is what the flow looks like today. You start with your RTL, which we support too today. Verilog, which is a very industry-tested solution that's been used for many, many years. And XLS. XLS is Google's high-level synthesis tool. And this lets you actually write and build hardware in C++ or Rust-like syntax. And this might be more familiar to software engineers who haven't worked with hardware as much in the industry. The next thing we do is we pipe this into Yosis. Yosis is our open synthesis tool. And this, again, will map our programming language into the tiny transistors and gates we need to represent that on silicon. Next, we take it to place and route with OpenRoad. OpenRoad's a project we're really excited about, and we've been supporting both with developer time and some funds. And it'll take our abstract representation of our circuits with AND and OR gates and put it on a silicon wafer. We then stream out the contents from OpenRoad into a tool called Klayout. Klayout will run some checks and make sure that we aren't violating any rules of the manufacturing process and emit our GDS file that we can take to Skywater, who's a foundry we particularly like, to manufacture it. So I mentioned that you can use Bazel to do this. And so something we've been investing a lot in is turning this large flow and complex process into simple Bazel rules. So, like I said, there's a lot of software involved in building hardware. And at Google, we know better than anyone that Bazel is an excellent tool to aggregate software from different programming languages and different compilers so that we can have a fully hermetic hardware build tool chain. And so we built all the open source tools in Bazel with our Bazel HDL repo. And we support two languages, as I mentioned before. We support Verilog and XLS. And we're really excited about XLS and its ability to reduce the amount of time it takes to develop a piece of hardware. So I want to show you a little bit how you can design your own hardware with our Bazel Rules HDL repo. Much like you would any Bazel rule, you load it and you can create a Verilog library. And so it takes sources the same way a C rule or a Java rule would take them, and we aggregate them all into this library rule. And so, as mentioned before, we're taking that counter.v file, and this is what it looks like. So what this piece of software or this piece of code does is it counts up one at a time every time the clock cycle goes high, and it'll reset once it reaches its top value. One important thing to note in this file is the top level module. In this case, it's counter. And so this is important as we need to specify a top module to our synthesis tool so it knows which part of our hardware we'd like to actually turn into reality. So next, we need to synthesize our Verilog library rule. We do this by first specifying that counter top level module I pointed out before, and then providing a dependency to our Verilog library rule. And you can chain these together in the same way you can with a Java rule, or a Java library, or CC library. And Bazel will take care of concatenating your sources and making them available to the synthesis tool. Next, we have OpenRoad, which is doing our place and route. So again, we load our rules from the location I mentioned above, and then we point it at our synthesis result. So once we do that and specify some other parameters like the clock speed, how dense we'd like it, and what size we'd like our silicon, we can build hardware with Bazel. So if we run Bazel build and wait about 48 seconds, we'll have hardware out on the other side. And so this def file is the output of our rules today. And you can actually take that def file into Klayout and view it. And like I said, in just 48 seconds, we built our very own custom silicon chip. And on the right, you can see what that looks like, containing all the transistors, wires, and hardware needed to represent our counter circuit. Each wire in this picture is about 130 nanometers wide. At that scale, you could fit almost 800 wires side to side on a human hair. And there's a little zoom in of one particular gate in our circuit. Well, building hardware in software is all fun and games, but I think we'd like to build our hardware too. And Google thinks it's important to support this community by getting it built for free. So Google started a project with eFabless to manufacture any open source design for free. We have multiple wafers going out every couple months, and any open source design qualifies. All you need to do is provide us with GDS, and we'll manufacture it and send you back parts. And you can go to that link below to find out more about what the exact submission criteria are. We also have built a Slack community with almost 2,000 members of varying degrees of skill, some who've been in the hardware industry for 20 to 30 years, and others just getting started. And we'd love to have you there. And we're in a very excited community. So if you have any questions, there's more than hundreds of members who'd be happy to answer them. The next thing I'd like to ask you is to contribute to some of the projects that I mentioned before. We have OpenRoad, who's doing our place and route, and it's a very exciting piece of software that has tons of algorithmic complexity if you're into that kind of thing. We have Yosis, who's doing our synthesis. We have Klayout, who showed us our pretty pictures and did some of the streaming for the manufacturing process. And then lastly, we have our Bazel Rules HDL repo, which lets us use Bazel to build our hardware inside Bazel. And lastly, that XLS repository is really exciting. I think it has a lot of potential to make it a lot easier for software engineers to design custom hardware. So please, if you have some time or are interested, check them out. Thank you.